Hey guys, so we are on video 2 of chapter 5. I am on slide 11, and we are just getting into all the calculations that relate to calorimetry. So we have a problem on the screen. How much heat would have to be absorbed to warm 240 grams of water from 22 degrees Celsius to 85 degrees Celsius? So to work this problem, essentially we just introduced an equation, Q equals MC delta T. We're solving for the amount of heat that is required, so that's going to be Q. I'm just going to plug my numbers in. The mass that we need is going to be the 240 grams. The specific heat, we are warming up water, and we said the specific heat of water is 4.184. Again, try to remember that number, 4.184 joules per gram per degree Celsius. And then delta T, if we're warming up the water from 22 to 85, the delta T is always the final minus the initial. So it's going to be 85 degrees Celsius minus 22 degrees Celsius. Once I have all that, if I multiply it out, that's going to give me Q. Now this is going to be a big number, 240 times 4.184 times 63. All right, so the number that I got, Q equals 63,262 joules. Now, a couple of things. Number one, sig figs. If we look at this number, it obviously has too many sig figs. The numbers provided in the problem, I think, had 2 sig figs each. So my answer ought to have 2 sig figs. That would make me round this to 63,000. And then often in mastering chemistry and just in general when we do problems, if it's going to be a really big number like that, they're going to tell you to convert it into kilojoules. If they don't specify, then you can do it either way. But if they do specify, you have to give them what they want. So I would expect this problem probably in mastering chemistry, they would expect you to write 63 kilojoules as your answer. Okay, so that problem is done. So now let's move to our next problem, where essentially I have a beaker of cold water and a beaker of warm water, and I'm going to dump them together. When I do this, I'm going to have a heat exchange where basically the hot water is going to release heat, the cold water is going to absorb heat, the cold water is going to get warm, the hot water is going to get cold, and they're going to meet somewhere in the middle. Okay? Now, it's not going to be halfway in the middle, because in this case, my warm water, I have a lot more warm water than cold water. So basically the warm water, since it's a lot bigger, it's only going to come down a little bit. The cold water is going to warm up a lot because it's a smaller sample, it's going to be more affected. Okay? So the setup for this though is, again, conservation of energy. Where basically I know that the heat lost by the warm water and the heat gained by the cold water are going to be equal to each other, except one's positive, one's negative. Technically, the one that loses heat, that's going to be the negative change. So I'm going to do the opposite. I'm going to change the sign of the negative one so that now they're truly going to be equal to each other. So mathematically, if you're going to set them equal, they either both have to be positive or both have to be negative. Okay? So when I set this up, I'm going to do for the warm water, when it loses heat, I'm going to use the equation to find out how much heat that is. The heat of the warm water is going to be MC delta T. And then I'm going to do the same thing on the other side. The heat gained by the cold water is going to be MC delta T. So I'm just going to plug in all the numbers I know and solve for the unknown. So when I look at it, the cold water, which is on this side, we said is 50 grams. The specific heat of water is 4.184 joules per gram per degree Celsius. And then delta T, I don't know the final temperature, but I know the cold water started at 22 degrees Celsius. So the delta T for the cold water is going to be TF minus 22. Okay, the warm water, the mass was 500 grams. The specific heat, again, for water is 4.184 joules per gram per degree Celsius. And then the delta T, remember it's always final minus initial. Now the final temperature for both waters, when I mix them together, they both end up at the same final temperature. So TF over here and TF over here are going to be the same. So I'm going to put TF right there, minus, and the initial temperature of the warm water was 80. So I'm putting that there. Now, essentially, I got to do the algebra. If you'd rather have, instead of TF, if you want to put X there, that's fine. I think on the next step I might do that. If I can find any ways to simplify before I start multiplying everything, I would do that. So I noticed that there's a 4.184 on both sides. And in algebra, if you have the same thing on both sides, you can cancel it out. So I'm going to get rid of that. And then I'm going to multiply in. So I'm going to get negative 500 X, the TF is my X, so 500 times that, minus 500 times 80. So a negative here, it's actually going to become a plus, and I think that's going to be 40,000. Okay, so that's that side solved, equals, here 50 times X is going to be 50X, and then minus 50 times 22 is going to be 1,100. Okay. Now I'm going to combine my X terms. I'm going to add 500X to both sides. So I'm going to end up with 550X on the right. And then I'm going to add 1,100 over there. So it's going to be 41, 1. And now I'm going to divide both sides by 550. And I got 74.73. X equals 74.73. Remember, X is a temperature, so that's going to be degrees Celsius. Now, my final answer, if I want to worry about sig figs, it's probably, I don't remember the numbers, but it's probably either 2 or 3 sig figs. So it's either 75 degrees or 74.7. Again, if you're reasonable with your sig figs on the problem like this, I'd probably be okay. We definitely, like, none of the numbers, the temperatures only had 2 sig figs. So if you leave 4 or 5 sig figs, I probably might count off a point, because I'd rather if you go 2 or 3 sig figs most of the time, that's going to work. If you're within 1 of the sig figs, you might be okay, but if you're off by 2 or 3 sig figs, then that's when I'm going to probably start taking points. Okay, so that's it for that problem. So now, we can use the equation Q equals MC delta T to deal with, like, we can find the amount of heat when we are warming a temperature, when we're warming a sample up from one temperature to another. Okay? This problem, though, is a little different. How much heat must be absorbed to melt a 25-gram piece of ice at 0 degrees? So there's only one temperature. Okay, 0 degrees, that's the only temperature that is given. So using the equation Q equals MC delta T, if there's only one temperature, you can't just plug in a T instead of a delta T. Like, that's not how the equation is set up. So when we're doing a phase change, melting ice, there's going to be a different kind of calculation that we have to do. Okay, we're still going to calculate the amount of heat, so we're still calculating Q, but we're going to do it differently. And basically what we're going to do, Q for a phase change is going to equal M times delta H of the phase change. Okay, now, that's a new term that we haven't seen before. Delta H is going to be the change in the enthalpy, which enthalpy is a word for the amount of energy stored inside the molecule. Okay, so delta H of a phase change will essentially, if you look in the appendix of our textbook, under Appendix B, it has a bunch of values that are related to water, which is the most common compound on Earth. When we do chemistry, water is almost always involved in a huge proportion of the problems that we do. So in that appendix, it tells you the density of water, it tells you the specific heat of water in the liquid form, the gaseous form, and in the solid form. And then delta H for a phase change, well, water can undergo two phase changes. The solid can melt into a liquid, and the liquid can boil into a gas. There's a certain amount of heat involved in both of those processes, okay? In order to melt a solid into a liquid, a certain amount of heat has to be absorbed by the sample. That value is called the delta H of fusion, okay? The word, we just say it's the heat of fusion. So the heat of fusion for water, again, it's in the textbook, but I think it's 6.008 kilojoules per mole. Okay? That's the amount of heat that it takes to melt 1 mole of ice. It's the kilojoules per mole. So water is H2O, the molecular weight is 18, so a mole of water is 18 grams. If I want to melt 18 grams of ice to give me 18 grams of liquid water, this is how much heat it would take. It's this much heat per mole. So if I had 2 moles of ice and I wanted to melt them, it would take twice as much as that number of heat. Okay? Now, the other value that we need to know is called the delta H of vaporization. And this is the one that if I want to take liquid water and boil it into gaseous form, I'd look that number up, 40.67 kilojoules per mole. Now again, you don't need to know these numbers, you just need to know how to find them when you need them. All right, so if I take the heat of fusion, because back to the problem we were given, we have a 25 gram piece of ice and we want to melt it. Well, I know that for each mole, it's going to take 6.008 kilojoules, so that number is going to go here. But then in front, if I have kilojoules per mole as my delta H value, then that means my M, in order for the units to cancel, the M this time, instead of mass, the M needs to be moles. Okay? So I'm actually going to have, for Q, it's going to be the moles times the kilojoules per mole. All right, so that's the equation that I'm going to use if I'm doing a phase change. So there's 2 equations. The first equation was Q equals MC delta T. That's the equation I use when I'm warming a sample up within one phase. Like if I'm warming up water from 25 degrees to 70 degrees, liquid water, water stays in liquid form that whole time. So I could just use that one equation. But as soon as I get to a point where water will undergo a phase change, which we know that water melts at 0 and it boils at 100. So if you're doing a problem that crosses through those temperatures, then you're going to have to deal with the phase change that occurs, and that's the equation you're going to use. Now, the delta H value, if you're melting, I'm going to plug in this number. If you're boiling, I'm going to plug in this number right there. Okay? And then the M just has to match up. If I have moles in my delta H value, then M has to be moles over here. If in the book, like in a mastering chemistry problem, if they gave you delta H in like kilojoules per gram, then I could use grams as my number in front. Okay? The key there is watch your units, make sure everything cancels out properly, and then everything works out fine. All right, so we can now work this problem. So I have 25 grams of ice. I'm melting it, so my phase change value is going to be the 6.008 kilojoules per mole. So I need to plug in not 25 grams, I need to change that into moles first. So separately, I got to say 25 grams times 1 mole over 18 grams I got to get that many moles. Let me calculate that real quick. So 25 divided by 18. It's 1.39 moles. So that's how much water I have. That needs to go in the front. 1.39 moles times 6.008 kilojoules per mole. Note that my moles cancel. So that'll give me my answer in kilojoules. So that times 6.08. So I got 8.34 kilojoules. So if I want to melt 25 grams of ice, then the amount of heat that would have to be absorbed would be 8.34 kilojoules. All right, so that's a good place to cut off. We'll pick up again